The universe thrives on chaos. It's in the messy swirls of a galaxy, the unpredictable weather patterns, and even the way your coffee cools down. This beautiful chaos is governed by a fundamental concept called entropy. Simply put, entropy is a measure of disorder or randomness. Imagine a perfectly ordered deck of cards, all arranged by suit and number. Now shuffle them. The deck becomes more disordered, more random. This increase in randomness is an increase in entropy. Entropy is everywhere, influencing everything from the smallest atom to the largest black hole. It's a fundamental principle that helps us understand how the universe evolves and changes over time. But entropy isn't just about things getting messy. It's a powerful concept that unlocks secrets about energy, information, and the very fabric of reality. Let's delve deeper into the fascinating world of entropy and see how it shapes our universe. Thermodynamics, the study of heat and its relation to other forms of energy, is where entropy takes center stage. Think of entropy as the director of a grand cosmic play, dictating how energy flows and transforms within a system. One of the most important laws in thermodynamics is the second law, which states that the total entropy of a closed system can only increase over time. In simpler terms, things tend to move from order to disorder, never the other way around. Imagine a drop of ink spreading in a glass of water. The ink molecules, initially concentrated, disperse and mix with the water molecules. This spontaneous process increases the system's entropy. The second law of thermodynamics, guided by entropy, provides a directionality to the universe. It's why we experience time moving forward, why broken eggs don't spontaneously reassemble, and why the universe is constantly evolving towards a state of greater disorder. Entropy might seem like a complicated scientific concept, but it's surprisingly relatable. We encounter its effects every single day. Remember that messy room we talked about? That's entropy in action. A clean and organized room represents a state of low entropy. Everything is in its place, neatly arranged, but leave it unattended and soon clothes pile up, books scatter, and dust bunnies gather. The room naturally progresses towards a state of higher entropy disorder. Another example? Melting ice. An ice cube, with its water molecules neatly arranged in a crystalline structure, represents low entropy. As it melts, the molecules gain energy and move more freely, increasing disorder and thus entropy. These everyday examples highlight a fundamental truth about the universe. Left to their own devices, things tend towards chaos. But don't despair. This natural tendency towards disorder is also what drives many of the processes that make life possible. We've established that things tend to get messy, but why? Why does the universe favor disorder over order? The answer lies in probability. Imagine a box with two compartments, one filled with gas molecules. If you remove the partition, the molecules will naturally spread out to fill the entire box. Why? Because there are far more ways for the molecules to be arranged randomly throughout the entire box than there are for them to remain neatly confined to one half. Disorder is simply more probable than order. There are countless ways for things to be messy, but only a few ways for them to be perfectly ordered. It's like flipping a coin. You're much more likely to get a random sequence of heads and tails than a perfectly ordered string of all heads. This tendency towards disorder isn't a sign of laziness or decay, it's a fundamental principle woven into the fabric of the universe, driving systems towards their most probable states. Let's revisit our melting ice cube. As we've seen, this simple process is a perfect example of entropy in action. But how does thermodynamics explain this transition from order to disorder? The key lies in understanding heat flow and energy. When an ice cube absorbs heat from its surroundings, its water molecules gain energy and begin to vibrate faster. This increased kinetic energy causes the molecules to break free from their rigid crystalline structure, leading to melting. The melting process increases the entropy of the system. The water molecules in liquid water have more freedom to move around compared to their fixed positions in ice. This increased freedom of movement represents an increase in disorder, and thus an increase in entropy. The melting of ice highlights how entropy drives processes towards states of higher disorder. It's a reminder that even in seemingly simple events, the fundamental laws of thermodynamics are constantly at play, shaping the world around us. Some processes in nature are like a one-way street. They only happen in one direction. You can scramble an egg, but you can't unscramble it. You can burn wood to ashes, but you can't unburn ashes back into wood. These are examples of irreversible processes, and entropy plays a key role in their irreversibility. Remember the second law of thermodynamics? It states that the total entropy of a closed system can only increase over time. Irreversible processes are those that result in a net increase in entropy for the universe as a whole. When you strike a match, you initiate a chemical reaction that releases heat and light, increasing the entropy of the surroundings. This increase in entropy is much larger than any decrease in entropy within the match itself. The overall result is a net increase in the universe's entropy, making the process irreversible. Irreversible processes highlight the directionality of time. They are a constant reminder that the universe is constantly evolving, moving towards a state of greater disorder, guided by the ever-increasing hand of entropy. Entropy's reach extends beyond the realm of thermodynamics. It also plays a crucial role in information theory, a field that deals with the quantification, storage, and communication of information. In this context, entropy measures uncertainty or unpredictability. The more uncertain or random something is, the higher its entropy. Conversely, the more predictable or certain something is, the lower its entropy. Think of a message written in a secret code. If the code is simple and easy to crack, the message has low entropy. But if the code is complex and difficult to decipher, the message has high entropy. Information entropy is all about quantifying how much information is contained in a message or system. The more unpredictable the message, the more information it contains, and the higher its entropy. Section 8. Flipping coins and rolling dice. Quantifying uncertainty. Let's illustrate information entropy with some familiar examples. Flipping a coin and rolling a die. When you flip a fair coin, there are two equally likely outcomes, heads or tails. This uncertainty about the outcome is what gives the coin flip its entropy. We can quantify this entropy using a mathematical formula, but the key takeaway is that the coin flip's uncertainty corresponds to a specific amount of entropy. Now imagine rolling a six-sided die. There are six equally likely outcomes, making the die roll more uncertain than the coin flip. This increased uncertainty means the die roll has higher entropy than the coin flip. These simple examples demonstrate how information entropy quantifies uncertainty. The more possible outcomes an event has, and the more evenly distributed the probabilities of those outcomes are, the higher the entropy. Section 9. Two sides of the same coin. Connecting thermodynamic and information entropy. At first glance, thermodynamic entropy and information entropy might seem like separate concepts. One deals with disorder in physical systems, while the other deals with uncertainty in information. However, these two types of entropy are deeply interconnected. Both thermodynamic and information entropy are fundamentally about unpredictability. In thermodynamics, entropy reflects the vast number of possible arrangements of particles in a system. The more possible arrangements, the more disordered the system, and the higher its entropy. Similarly, in information theory, entropy reflects the unpredictability of a message or event. The more possible messages or outcomes, the higher the uncertainty and the higher the entropy. This connection highlights a profound link between the physical world and the world of information. It suggests that the fundamental laws governing disorder in physical systems also govern uncertainty in information. Section 10. Why entropy matters, from coffee cups to the cosmos. Entropy might seem like an abstract concept, but it has profound implications for our understanding of the universe and our place within it. Entropy dictates the direction of time, the fate of stars, and the evolution of the cosmos. It influences the efficiency of engines, the flow of heat, and the transmission of information. Understanding entropy helps us appreciate the delicate balance of order and disorder that makes life possible. It reminds us that the universe is constantly evolving, moving towards a state of greater randomness, and that this evolution is a fundamental aspect of reality. From the smallest atom to the largest galaxy, entropy is a guiding principle that shapes the universe we inhabit. Section 11. Keep exploring. The journey into entropy continues. This exploration of entropy has only scratched the surface of this fascinating and multifaceted concept. There's much more to learn about its role in black holes, its connection to the origin of the universe, and its implications for the future of life itself. I encourage you to delve deeper into the world of entropy, explore its mysteries, ponder its implications, and marvel at its profound influence on the universe we call home. The journey into entropy is a journey into the heart of reality itself. It's a journey filled with wonder, discovery, and a profound appreciation for the elegant chaos that governs our universe.